In this video, I'm going to talk about continuity, but for polynomials and rational functions. But before I do so, let me kind of define what polynomials are. Polynomials are defined as follows, by the way, guys. P of x, normally that's the notation we use for polynomial. P of x is equal to a sub n, x to the power n, plus a sub n minus 1, x to the power n minus 1, plus a sub n minus 2, x to the power n minus 2, plus dot dot dot, plus a sub 2, let's say x squared, plus a sub 1, x, plus a sub 0. This is just the general structure of a polynomial. This is called nth degree polynomial because the highest power of x is n here, where n is a positive integer, okay? So, having said that, we kind of want to show that polynomial functions are continuous. Just so you know, polynomial functions are continuous everywhere on the real number line, which means that it is going to be continuous on the interval from negative infinity to positive infinity. So, the entire number line, okay, entire number line. Now, let's go ahead and show that this is continuous. So, how do we show that? Remember the definition of continuity at point A, let's say. Our point of interest is point A, is going to be limit x approaches A, f of x, but instead of f of x, we are going to have p of x here, right? We are using the notation p of x to indicate that we are dealing with polynomial function. And this, by the way, should be equal to p of A. That's what it should be. Based on the definition of continuity. And it's very easy to show, right? Polynomial, limit of the polynomial function, limit of x approaches A, p of x is gonna be limit of this first term, limit of this second term, using the properties of limit, right? We can do it that way, one by one. So I'm just gonna write it out one, maybe limit x approaches A, a sub n, x to the power n, plus dot dot dot, plus the last one, very last one I'll write down, limit x approaches a sub 0. Now please don't be confused by these notations. It's very simple. It just looks like a lot mathematical than it is, right? It's very simple. You are just applying the limit definition. So limit of the sum is sum of the limits. Now let's just take any one of them. So limit x approaches a sub I, okay, x to the power I. All right, where I is an integer between 1 and n, okay. So I is an integer between 1 and n. 1 and n. So this is a constant, so we could just pull it out. So there's going to be a sub I limit x approaches a x to the power I, right? Which, by the way, is a sub I times a to the power I. We know that x raised to the power n, limit of this as x approaches a is a to the power n. So this is what it is going to be. So this limit exists for each of them, right? For each of these terms. And finally, the limit of this guy, limit x approaches a sub 0, which is just a constant, is different from a, by the way, okay? It's not impacted by the value of x because this doesn't have any x term in it. So this must be just a sub 0. So now, if you take all of this information into consideration, that means individual limits, you notice very quickly that limit of this thing is nothing but p of a, which is like plug in a for x in each of these limits, you're gonna get the limits. So, and it turns out to be that it is p of a, which is just this. So very simple and straightforward. So this is a very important piece of information and a very useful one because polynomial functions, we use them a lot, right? So polynomial functions are continuous everywhere on the number line. And similarly, rational functions, okay? If you have rational functions that are continuous, so let's say you have p of x, okay, and q of x. These are two rational polynomial functions. The ratio of these two are also continuous, given that q of x is not equal to 0, or q of a in particular is not equal to 0. So I hope that this discussion was helpful. Thank you very much.